Hi, in this video we will go through the properties of matrix addition and scalar multiplication and sketch the proof of the ideas of the proof of these properties. Okay, let us start with the assumption assuming that A, B, and C are matrices of the same dimensions, and also we have scalars, and let C and B be scalars. Then the first property that comes up is that if you add A to B, it is the same thing as adding B to A. In other words, the matrix addition is commutative, and the property is called commutativity. And to see how this is possible, everything is because these two operations are done entry-wise, and if you're looking for ij entry of this guy, this is basically ij entry of first and then ij entry of the second, but these are just two numbers, and in the numbers we know that we can switch the order, so it means that I can write this in different order, yeah. And this is the same thing as the entries of B added to A at the position ij. So that's the first property, and then the second property is another thing that helps us to work with the matrix addition very nicely, and this says that if you have three matrices, if you want to add them, one can start first adding two and then adding the result to the third one, or you can add last two and then add the result to A, to the first one. These are going to be the same thing. This is called associativity. And what this has as a result is that, when you have matrix addition, you don't need to be worried about the brackets. Just do in whatever order you like, if all of them are addition. And how to prove this again, A plus B plus C, if you're looking for ij entry, this is going to be ij entry of A plus B added to ij entry of C, but this guy is the same thing as aij plus bij then plus cij. But these guys are numbers. In the numbers, associativity holds, and then we have aij plus bij plus cij, and this is same thing as, this is A plus B plus C entry ij. So each entry, these are going to be the same thing. Furthermore, we have more properties that, if you add any matrix to zero matrix, this is, you get back the zero matrix. This is obvious how this holds. And then if you add a matrix to its inverse, you will get a matrix which has same dimensions as A, but all the entries are 0. Then the next properties are relation between the addition and scalar multiplication. So how these two things work together? If you add two vectors first, then scalar multiply a constant to it, you will see that this constant goes in and distributes over these guys. So this scalar multiplication distributes over matrix sum. And this is again, you can just easily show that ij entry is what? Ij entry is C times aij plus bij, and these are just numbers, and we know that number multiplication distributes over number addition, so Cij plus Cbij, and this is the same thing as Caij, ij entry of Ca and ij entry of Cb, and that's what we have now, Ca plus Cb ij entry. There is also another distribution, so let me just write the distributivity here. This version is scalar multiplication over the matrix addition, but the other way also works nicely, meaning that if you have two scalars added, then scalar multiply to matrix, then this will happen also again. So this will be the same as Ca plus dA. The proof will go exactly same way with a little bit different one. So this is also another version of distributivity, and as you see this time, scalar multiplication distributes over the scalar addition. Also, another property is that, well, if you scalar multiply a number to a and then scalar multiply another number, this is the same thing as you first do scalar multiply and then you multiply the scalars and then scalar multiply to a. Okay, and the property which is now I hope it's obvious that if you multiply 1 to a, you get a, and if you multiply 0, the numbers, their scalar 0 to a, you get 0 matrix. Okay, so these are the properties, and as you can see, it's not something different than just numbers and also vectors. We will get back to these properties and we will see that how this makes matrices kind of vectors in another video. Okay, so let's just use these properties and do at least one example. Solve the following matrix equation. An equation is given. There is a matrix X missing, or as the variable, and now we have to find this. So how do we do this thing? So I will write all the steps here. I want to bring this guy to the other side, but what does that mean? That means that I add both sides by the negative of this matrix. And well, let me just multiply this in. Oops. Six, 3, 9, then plus negative 1, 0, 2, negative 1. And this gives us 2x plus, well, a matrix added to its inverse, this is going to be 0 matrix, equals, and then this is subtraction of matrix, negative 1, 6 minus 0 is 6, 3 minus 2 is 1, and 9 minus negative 1 is 10. Now we know that if you add a 0 matrix to a matrix, you get that matrix back. This is the property. What number was that? The third one. Yes, this is the third one. And this guy here, the way we did from this to there, this was the property that you add any vector to any matrix to its negative, you will get zero matrix. Now we are almost done. We can multiply both sides by the inverse of the coefficient. And the property that we had, the actually it's here, just the seventh property says that says that, well, I can multiply these two first and then scalar multiply to x. With this side on the right hand side we get these things, but this guy is 1 and 1 times x is x itself. This is another property that we had. So you can do exactly same steps as before, just keeping in mind that we are now working with matrices rather than just scalar numbers. Okay.